Hello and welcome to the video. In this video, we will look at the problem swap nodes and algo in the square brackets. So we have almost solved 34 problems in the Hackerrank interview preparation kit playlist. You can check here. And we swapped many things. We swapped array elements, we swapped map elements, girlfriends, no girlfriends. So let's start with the problem. First, this will be a problem definition, then explanation and the code. I'm quite sure this will be a two-part series because there are so many things which I need to explain. So first will be more consist of explanation. Second will be how the input is being taken, and then the code. So let's start. So before again starting, I need to give a small disclaimer. I usually don't give it because this particular problem is mostly based on the trees and then search. So if you are someone who knows basic things about trees, so it will be enough. I'll be covering this particular problem in the depth. So if you know the basic like left child, right child, what is the road, that is enough. We will cover this. However, if you haven't come across trees as of now and don't know anything about trees, I would request you guys to once look upon the trees section or tutorials. I'll be adding links which might be helpful. Do read them, and after that check the video so you can grasp all the concepts. Okay, so let's start. First is the problem definition. In this particular problem, if I summarize this particular problem, we will given the input. So input is in the format of number of nodes, which is followed by test cases and then k value. So I'll tell you what each thing is. Let's consider we have a binary tree. Let's assume this a binary tree. So let's consider this as 1, 2 and 3. So we will be given input. After that we will form a binary tree like this, and after forming the binary tree we will get the value k, and k is the value which represents level at which level we have to do the swapping. So let's assume we get the k as 1. So we know the level 1 is this, and the swaps which will occur will be 3 will go here and 2 will be here. So the whole or the solution for this particular problem will look like 1, 3 on the left child and 2 on the right child. After this we have to give output in the terms of in order. So I'll be explaining what is in order, pre-order and post-order. I'll also give you the basic technique which will help you remember for the lifetime what these three things are. So the basic problem is we have to convert the input to the tree. After tree, for the given k value and all the multiples of k, we have to swap the values. After swapping the values, we have to print out the in order transversal of that particular tree. Okay, so this is the problem definition. Let's start with the explanation, and let's address the elephant in the room. So how we will create this particular tree, how we will visit each node, and how the transversal will work. Okay, so let's start with the explanation. So let's start the explanation. First we'll look at the binary tree basics. So this is a binary tree looks like. It can have two nodes, that is left child, right child, or a zero node as well, or zero child as well. So first we have root, then left child, right child, similarly right child, left child, right child. And you can read more about the binary trees. I will be adding links so you can read that. After this we have to check for what is in order, pre-order and post-order. So I'll give you a trick here. So let's consider you have to give the pre-order of this particular array or tree. So what you will do is you will protrude one line on the left hand side which will represent a pre-order. Okay, now what we need to do is we need to connect these lines. So first we will encounter one, that is root child. So this is for pre. So pre-order for this given tree will be 1, 2, after that it will hit 4, after that it will go inside, then 5. So let me write 1, 2, 4, 5. After 5 it will go inside, then 3. Okay, so this was a path for a pre-order. Okay, so if I check for the post order, let's say, so that for post order the line will be here, and in this particular problem we are looking for in order. So the in will be in between or in the straight line downward. So pre will be here, in will be here, and the post will be here. So let's draw the lines. Now let's start with our path. So no lines is met. First line we get is 4. So for in order, first element we get or first node we get is 4. After 4 it will be 2. After that it will be 5. After 5 we will again go, then this will be 1 and 3. So I hope I have cleared what is a pre-order, what is in order, and how you can derive it. For post order, the lines will be drawn on the right hand side of each element. So I'm assuming you got the logic and can draw in order, pre-order and post order things. Okay, so as of now we saw the binary tree basics. It's not much of basics, but that's what I've written. So we saw what is in order, pre-order and post order. It is required because we have to give the output in this particular fashion only. Okay, now that we have seen two basic things, let's move ahead how we will create this particular binary tree and how we will transfer into the tree. So there are two popular methods by which we can do, that is BFS, breadth first search, second is depth first search. In breadth first search we go horizontally or level by level. So if you see, for breadth first search, first we will encounter 2, after that we will encounter 3, and after that only we will hit the next level. So here we go level by level. You can also call it a level order transversal. However, in the depth first search, what we do is we first visit the node, again go in the depth, check its child node, again after 4 we will hit 5, then again we'll come at 2 and then visit 3. So this is the depth first search, and if we go level by level it will be breadth first search. So the I think depth first search has a quite or a slight advantage over breadth first search in this particular problem. However, I think breadth first search is very easy to explain. You will get the concept very easily because we have to swap the elements on the same level. So it is very intuitive to go for a breadth first search because we will be on the same levels where the swapping will occur. Okay, and I have added links of gigs for gigs, the difference between what is breadth first search and depth first search. And how you can implement it on the various data structure and what is more useful. So you can read that article. And as I said, we will be using BFS, and after this we will look for swaps. So now let's move ahead and let's create our tree. How the we'll check the input, and using that particular input we will create tree, and after getting that particular logic only we will look at the swapping. Okay, so let's start. So let's start understanding BFS and how we'll use this particular input, given input, in our favor to create the tree or the tree elements, and then we'll look at the swapping. So how we do the BFS is, first let me write here. So first we visit the node. So visiting any node which is present, and because in this particular BFS we generally use queue data structure, and in DFS we use generally stack. So in queue we can dequeue it or we can pop that particular value after visiting, because we will check how many further values which can be enqueued here. After that, visiting node, we will check for the left child. If left child is not equal to null, then we will push a new value into the left child. Similarly, for the right, we will check if the right value is not null, then again we will push the value into the right child, and the not null value or null value can be represented in this particular example by -1. So if it's a -1, that means there is a no node on the left or right hand side, so we can use it accordingly. So let's understand the input as well. So this is n number of test cases, and these are the 3 nodes, right? So it will be first node, second node and third node. First node will be always root, so it will be 1, so you can call it a 0. After that, first, second, third, and this is the number of test cases, and this followed by k values 1 and 1. So let's start. So using this particular given structure, we will create 2 arrays. So first will be left array, which will store the values of left childs. So in this particular array, let me create it quickly. I think there are 3 values. So it will start with 1 based index. Why? because first value is always root and it equal to be 1. So first value will be 2. So I think this is input as A and B. So A will be of left child and B will be always of right child. So 2 minus 1 and minus 1. Similarly, on right hand side we will store 3 minus 1 minus 1. So we have created 2 arrays. Okay, so please stay tuned. So if you are having a doubt why we chose array, because the operation on array is very simple. So what we are trying to achieve is, rather than creating the whole tree and then doing the operation on it of swapping, we want to save the position of a tree into left and right array and do the swapping on the array only. So this saves a lot of time in the terms of time complexity as well as in the space complexity and overall the complexity of the problem. So on the right hand side it will be 3 minus 1 minus 1. So as we discussed, we will be using Q in our data structure. So Q has a first in first out what we can say property. So here what we will do is, we will declare some variables. I'll explain you what are those. First is Q, which is required. Then we'll have a level. It will tell us on which level we are, because we are using a breadth first. We want to know on which level we are so that we can do the operation. On each level, we need to know how many count of nodes are present. So let me explain it real quick. So let me write it first. So here I think I should scrap down Q BFS, because I'll write Q here, level here and count here. So let's start explanation. So we know that the things which we will require, that is Q, level, count. We have created left array and right array which holds the value of left childs and right childs, and we know the basic formula. Visit a node, pop up the value, check if the left value exists. If yes, push the value. If check if the right node is not null, yes, then push the value. Okay, so what we'll basically do, I'll write a basic pseudocode here so that you might not get confused or get a help. So first we will initialize Q, right? And after initializing Q, we will push the value 1, because the root node will be always 1. Okay, after pushing value of Q or root into the Q, we will increment the level. Okay, so let me write as a level plus plus or LVL plus plus, because we would be incrementing into the level. First it will be 0, and after incrementing by 1 it will be 1. Okay, after this I want to do an operation while our queue is not empty. So as long as we have elements in our queue, that means we need to create or create the whole tree. So what I can write is while not equal to q dot empty. So I hope you are getting this. Okay, while q is not empty, I'll do certain operation. What will be those operation will be, first I'll increment the level. After incrementing the level, I'll check how many count it has in the queue. So count will be given by the size. You can always say a size for this. Now what I'll do is, again I'll check for how many elements are in the level, and which will be given by count. So it will work as while count minus minus. So please be rest assured, this is not the code. I'm just simply writing because it helps in the flow. So we will decrement the count, and for each count we'll do these 3 operations. Okay, so we will pop out the value from the visitor node. We'll check if the left node exists. If it's not null, we will push the value into queue. Similarly for the right node. So let's start afresh. So we know that we have first node, and let me do this thing, and this is represented by this. Okay, so you get the whole link. First we are on the first level, so we checked how many count present. So as of now queue we only have 1, so the count will be 1. So while this while loop will run 1 number of time. So we'll visit the node, and by visiting I mean doing something like, let's say we take the value in any form, let's say B or P. P works because P and Q. So we'll push or pop the value from front. We'll get the value into integer of your choice, and after getting the particular value we will pop the value, because we want to do further operations, we don't require this particular value. So as of now in our queue we have only one element, right, that is 1. So the p will have value that is 1, right. For p we will check in the left array, because we know that our left array and right array start indexed from 1. So as p is equal to 1, we'll check if this particular value is not null. Yes, it is not null, we know it is 2. So in that case we will add a node here, 2. Okay, after this left node is done, we will go to the right node. We will check if it's not null for p's value. So what we are checking at, for this particular value, do we have any elements in the left left array and the right array. So in this case we have value that is 3. So we will add this 3 here, and by adding I mean pushing these values into the queue. So we have popped the value 1, so this will be removed, and let's assume that our popping is done from here. So it will be 2 and 3 at present. So we have added 2 here. Similarly for here 3 added in queue. So one while loop is done, because count was only 1. So this whole operation is done. After this we will increment the level. We will go at the level 2. Okay, after going on level 2, as still queue is not empty, so we are still in this particular loop only. So level is 2. So we'll check how many counts for size. So we know as of now there is 2 and 3. So the count will be 2, because for each node we have to check, right, left and right. So after this the whole loop will run twice. So again let's check. For first value, the p value will be q dot front and q dot pop. So first value will be popped and the current p value will be 2. So let's take p somewhere. So I am taking p here. So p is now 2. For 2 we will check if it's null or not null. In this case we can see -1, and in the problem definition they have given if -1, that means there is no node. So we will not be adding any left child to 2. Similarly we will not be adding into the queue. Okay, after that, because we have count 2, and we'll check for the right. Similarly for right it's -1. So again 2 will not have a right child. Okay, similarly the count was 2, so one loop was done. Now again one loop is remaining, and that is for 3. So for 3 the value will be popped out. So p will be 3 in this case. For 3 we will check what are the values. So in the left child we have -1, so we will not be able to add here. Similarly for right child it is a -1. So again we cannot add any because it's a -1, there is no node, we cannot add. So in the end and 3 is also popped, right, for the whole count. So in the end we get this particular binary tree, because this is a simple example, I know. So similarly we can integrate the 4 and 5 here as well, the next example. So what will happen is we will be adding extra elements here, again there, and the whole level and count will be increased. So by now I'm thinking, or I'm assuming you got the logic. So let's reiterate, or let me summarize. We are using BFS. BFS use Q. Level is our variable to check at which level we are, and count will give us how many elements are on that particular level using Q dot size. This is the basic pseudocode. We will initialize Q, we will increment the level, and we'll take the while loop. While Q is not empty, we will be incrementing two values or checking two values. That is, first is level plus plus, then checking count, and for each count we will be doing visiting, popping out the value, check for the left node, check for the right node. If yes, push those values into the queue. Similarly, this is a more of a pictorial representation. However, our main tree lies here, right? So push that values into the queue, and after doing this we will get our final binary tree. Okay, so by now I'm still assuming that you got the logic. After this, what we have to do is the swapping. By now we have saw binary tree basics, in order, post order, pre order. We saw what is the difference between I think color is black. Let me recorrect it. Okay, we saw what is BFS and DFS. We are using BFS with queues implementation. We saw three basic things, that is queue, level, count, and how BFS will work. Now let's move ahead with the swapping. And for this we will know why we took level. And swapping, we will be given value k, and we have to do the swapping in k's multiple values. So it will be k, 2k, and 3k, and similar. So if you look closely, we have answer right here only. For swapping, what we will do is, we will check k, and we know that we need to have the multiples of k. So it is the importance of level terms. So what we will do is, because there will be level plus plus here, and I think a count I have said earlier. So these two terms will be here. So what we will do is, we want to swap elements at k, 2k, 3k, and what k is a level, right? So what we will do is, we'll write a simple loop. So this was for previous. So what we'll do is, we will simply do a level and mod it by k. So that means if level is multiple of k is equal to 0, so that this represents the whole statement. If level is a multiple of k, I want to do the swap. So you can write a basic swapping logic here, right here. You can always write above the blue statement, there is no issue. So you will write the swapping logic. So what swapping logic will be, let me write it here. So swapping logic will be containing the left and right elements. We don't want to interfere into the tree. We want to change the left and right array, and after that we will do the inorder and inorder, pre-order, I think only inorder on the array, so that we save a lot of things. So the swap logic will be a basic swap function to change from left array and the right array. So swap will work. Let's say we were taking values p. So what we will do, we will check if the level is multiple of k. We will simply swap left of p to the right of p. That's it. That's the basic simple swapping. So I know it could be confusing for starters. However, you need to learn the BFS. Once you learn the BFS, the swapping is very simple. We are changing only the left and the right array, and these two values into the swap function. So right p, okay, these two are in the swap function. So what we are basically doing is, so in the particular problem, above problem, it was 1, 2 and 3, and the given problem is k, or the k value was 1. So we know that we need to do something swapping here on first level, because there is one only level. So what we will do is, we will do the swapping here, and we know that it is a 1 based index. So 3 will be shifted here and 2 will be shifted here, okay. And when we are doing inorder transversal, what we will do is, first we will apply inorder on the left array, after that we will print out the value, and then inorder on the right array, okay. So after first iteration, we will get the inorder of the given tree. So let me I think it's very cluttered, so let me clear some things and then I'll explain. So if you see, we draw this 1 2 3. After first swap, it will be 1 3 2. So in order for this will be 3 1 2, and again for one more test case, again the elements will be swapped and it will be 2 1 3. Answers are here. I wanted to take the test case, this test case, because it's have quite few elements. However, due to space crunch and also time, it will be a longer video. And if you haven't got a bits of the whole explanation, please be rest assured. Again, I'm making a coding video on this. I'll be live coding it. So I'll explain few more things which might be difficult. So please be rest assured there. So now let's understand how we will print the inorder output for this. So we understood what is inorder, pre-order and post-order. Let's work how we can use that particular statements on the array and then get our desired output. Okay, so let's start. Okay, I have written the basic coding for this because it is recursive, and for the last explanation I was running out of space and I didn't want that to happen for this particular explanation. So I have basically written the code. So let's start. So we know as of now our the tree is 1, 2 and 3. So after first swapping, we know it was resulted into 1, 3, 2. So it became 1, then 3 and 2. Now we need to print out the values. So we saw how Inorder will work. We put values into the in, and then again we'll go for this terms. However, how will this work in our left and right array? So there is one correction. After doing the swaps, the new array will look like 3 minus 1 minus 1, and it will be 2 minus 1 minus 1 because we swapped first value. Okay, so please bear these things in mind. After this, what we will do is, first we will use a recursive Inorder. We will call it on root. If root is minus 1, we will return. If not, we will Inorder on the left root, then print out the values, and then again do a Inorder on the right node. So I have used basic simple C code. So here first check. As of now, first we will come as root will be always passed as 1 first. So first we will check in order of left root 1. So at first we have value 3. So we will again, it will be passed as in order of 3. So here root will be 3. Again we'll check if there is value at level 3. So this is 3, 2, 1. So it's minus 1. So it will be returned. After that we will go for the print statement. It will print the root. As of now the root's value is 3, right? After this we will go for in order right root. So we'll check if there is a value exist. Now let's start. I have written the code because in last explanation we were out of space crunch. So I think there could be issues. So I wrote it down. So in this particular Inorder, we are doing Inorder on left and right array. So from the last explanation, we know we did one swapping, and the resultant right and left array will be 3 minus 1 minus 1, and it will be 2 minus 1 minus 1 because we did one swapping, right, on the first level. Now we will implement this function in order on the root value. First root will be passed as 1. So we'll check if it is a minus 1. If yes, we will return. If not, we will use this logic. First we will go in order on the left root. If not, so it will go till it gets the minus 1. After this we will print out the value of root, and after that we will do a in order on the right root. So let's check one or two example. For first value will be passed. So it is we'll check if it's minus 1, no, we have value 1. So left root 1, so we know it's 1 based indexing, so the value will be 3. So again in order of 3 will be called. So we'll check root is not equal to minus 1. So again we'll come at this particular position. So in order left and root 3. So yes, it is a minus 1 in this case. So this particular statement will return false, and after that we will hit the statement print statement. Here we will print out the root. As of now root has the value of 3. After this we will call in order right of root. So as of now root value is 3. So right of root will be minus 3. So it will again return. After this again the root will be called, and the following input will be 3, 1, 2. So this was for this particular tree. So it was 1, 3, 2. So in order will look like this for this case. Similarly in the test case we have one more swap. So again if we swap 2 and 3, the next input will be which we saw by using this particular technique where we can connect these dots. So next input will be 2, 1, 3. And I think these are the answers. So in this particular problem what we saw is, first we saw the binary tree basics. We saw what is in order, post order, pre order. We saw what is BFS, DFS. We are using BFS. Why we are using it? The number of things which are involved is in this. After that we saw swapping. Swapping will be done for the k multiples, and we'll check if the current level or the level at which are we at in the binary tree, if it's multiplicative or multiple of k. If that is the case, we will do the swapping in an array, and after that we will print out the result. So I think this is enough for this particular case. I know could be quite confusing if you are looking at or solving it at first time. So let me know in the comments if there is any doubt. I would be more happy to solve the doubts, because writing is more of natural to me than saying. I'm quite introvert. So do let me know if there is any issue. I'll write down in the comments to help you more. And in the next video, we'll focus more on the coding. And in that particular coding, I'll again look at how input can be transformed into the given tree, and then we'll do the swapping. And similarly, for each line, I'll be trying to add comments where I feel there could be a issue for you guys. So let me know if there is any issue. I'll be more happy to solve. So keep watching and watch for the second part. And thank you for watching. Have a great rest of the day.